We'll talk about the general approach to shaft design, utilizing all of the fatigue failure theories we've been discussing for the past week. This shows an example of a commercial gearbox on the back end of a rather big engine. I don't know what that came out of, but the gearbox is just this piece right here. And the input and output shafts are in line with one another. If you remember from kinematics, this is of the class compound reverted. Compound because there are two stages, reverted because the input and output shafts are in line with one another. So you can always tell the input and output shafts at a glance because they're different size. The input shaft is smaller than the output shaft, and why would you presume that to be so? What's different? More torque on the output side by whatever the gear ratio is in the box. So I have to have a larger shaft to handle the torque and keep the stresses down. So this is the input side, a pinion right there, and mesh with a gear, which is on the same shaft. This is called the jack shaft, with another pinion driving another gear, which reverts back to the original center line. So from the outside, you see a box with shafts coming in and out that look like they might be the same shaft going through, but they're not, because it goes through this power path inside the box. This shows tapered roller bearings mentioned in the legend above. You see here and here in pairs supporting this piece of shaft, which is separate from this piece of shaft. So two bearings give me a moment, a couple, and this is one piece shaft, so you have a bearing at this end and a bearing at that end. Tapered roller bearings are often used in the front wheels of your car, not exclusively. Some car manufacturers use ball bearings, but this is common. And they're able to take very high load, and they are able to take axial as well as radial load. We'll talk more about bearings in a subsequent lecture. This shows another example of a shaft in some big planer metal cutting machine, really long shaft. Here we have self-aligning ball bearings at the two supports, and those are sort of spherical inside on the race, so that if there is any misalignment between the two mountings for the two bearings, this will accommodate it and not put an extra moment on the shaft. So it's very common to use self-aligning bearings of this sort in shafts and other applications as well. So there's an overhung load with an input pulley and some kind of a gear there. So here's some general guidelines, rather a long list. We'll go through it step by step. You may have constraints on stresses, usually you do, but you may also have constraints on deflections, and those are very different situations. In general, if I want to limit deflections to low values, I will probably end up with pretty low stresses, because having low deflections is a more severe and difficult requirement that usually ends up with a bigger shaft than I would have to have if I just didn't want it to break. Okay? And that's true not just of shafts, but everything in general. If I design for deflection, I usually will end up with a very good safety factor against stress failure. But I can minimize both stresses and deflections by keeping the length short to reduce the bending moments. Cantilever configurations typically have larger deflections than what are referred to as straddle mount or simple support. So if I have my choice in a particular situation, I would much rather have a straddle mount, so-called, that is my loads in between my supports, or rather than a cantilever. So if I can manage it, I will do the former. Quite often you have both, as in that long shaft I just showed you, where there was a pulley hung out on the end. So that's an overhung load on what amounts to a cantilevered portion of the shaft, and the other load was the gear in between the two supports. That's properly called an overhung shaft, because it's like a cantilever in that I have a cantilevered piece out, but unlike a cantilever, which has a moment joint at the wall and thus has a zero slope on the beam, I can have a non-zero slope in an overhung because it's going to belly up or belly down in between the two supports because there's another load in there. Hollow shafts can be used to get a better stiffness to mass ratio. In other words, it will be lighter. You could make it bigger in diameter to recover the lost cross-sectional property. The J obviously will go down if I hollow it out and don't make it bigger. But since the J the polar moment of inertia is a function of diameter to the fourth power. If I hollow it out and add a little bit of diameter, I can pick back up what the lost stiffness of the center, because that was at smaller radii, and thus it didn't have as much effect, much like a flywheel, which is radius squared. This is radius to the fourth. They're expensive because I got to somehow get rid of that metal in the middle. I'd like to minimize stress concentration, particularly where I have high moments, and thus high bending stresses. But the bottom line is I can't really get rid of all the stress concentrations. The only way I could would be to make a shaft that's perfectly the same diameter over the whole length, has nothing attached to it. So what good is that? So as soon as I want to put a gear on with a keyway, I get stress concentrations in the keyway. If I step the shaft so I can put it up against the bearing, stress concentration in the step, and so forth and so on. So I can't get rid of them. All I can do is minimize them. It turns out that I'd rather have low carbon steel when I'm designing shafts subject to minimum deflection. Why? Because the strength of the steel has nothing whatsoever to do with deflection. Look at the deflection formula. The only material property in there is modulus of elasticity. Young's modulus if it's a bending problem, and shear modulus G if it's a torsion problem. Strength does not enter into deflection at all. So if I'm going to design for low deflection, I can use low quality, low strength steel, which has the same Young's modulus as the expensive stuff, and I will have low stresses because of the low deflection, and thus I won't run into a problem of breaking the shaft with high stresses. Shafts often have gears on them, and at the gear, if I have any significant deflection in the shaft, then that gear is going to not mate properly with the other gear, which is on a different shaft, right? And I will start to wear the gear teeth out in a hurry, because what I would really like to have is nice line contact across the width of the gear, so I distribute the load and get good wear. So if I'm cockeyed, I'm going to ride on one edge of the gear, corner to corner, and I'm not going to get good wear. So there's some parameters for that. You see them here. 5/1000ths of an inch is the most deflection we would like to have at a gear set, and I don't want the slope to be more than 3/100ths of a degree. And those are pretty severe constrictions, and that's why I would have to design for deflection in this case. And of course, this is the slope of the deflection curve, right? The angle. So if I get that the deflection is low, the slope should also be low. If plain bearings are used, now by plain bearing is meant not a tapered roller, not a ball, not a roller, but rather a chunk of metal that looks like a big donut through which I put the shaft. And they're made of different materials. We'll talk about that in another lecture later on too. So materials that like to run well together and so forth. And now what I'm going to do is make a very nice fit between the hole and the shaft. Typically I'm looking for like 1/1000th of an inch clearance on the diameter would be ideal. Just enough to support a thin film of oil. And if I have that low a clearance, if there's any deflection or slope, worse than deflection is the slope, right? But that's because of the deflection over here. Then I'm going to grab that bearing on either edge, right? And I'm going to run the friction way up and the wear up, and I'm going to start to egg out the bearing at both ends, and it's going to look like an hourglass after a while. So I have to limit the slope through a plain bearing to about 4/100ths of a degree. That's a small angle. If plain bearings are used, deflections at the gear location should be less than the oil film thickness in the bearing. We'll get to that in our lecture on bearings coming up sometime soon, which is an interesting study in itself. But as a little preview of coming attractions, the way it works is the shaft is water skiing on a film of oil with no contact between the metal parts. And that film of oil has to be a certain thickness. It won't work if I have too much clearance in there. And I don't want to deflect my way through the film and then get into metal-to-metal contact. The first natural frequency of the beam should be 3 times or more than the highest frequency expected in service. We'll look at that briefly as well. It's in this chapter 10. And there are standards associated with gear shaft design, ASME, AGME. You know what ASME is. You probably are a member of the student division of Mechanical Engineer Society. American Gear Manufacturers Association is what this guy is. And that's a sort of a quasi-commercial. It's not a government agency by any means. It's private. Gear manufacturers pay money to it, and the organization does research to better understand gear technology. They set the standards. We'll talk about those more when we talk about gears later on. So we can have any one of the flavors that we've talked about of loadings in a shaft situation. It could be fully reversed. It could be repeated, meaning it's going from 0 to something, or it could be running around up here in between two different values. Same slide I showed you before when we started talking about this kind of dynamic loading. I think you already understand from what you've done in your project that even if I have a constant load crossways on the shaft, constant force, say a belt on some pulley, and I have a net force, one side of the belt's tighter than the other, and the difference between the two is the force I'm pulling sideways on the shaft. Let's assume that's constant with time. That doesn't give me a static loading in the shaft, because the shaft is turning such that at one instant this little piece of shaft is in tension, then it's in compression, then it's in tension, compression, tension, compression, and so forth and so on. So I get fully reversed stresses with a constant load or a constant moment on the shaft. So that gives me this particular case, fully reversed. So I just said right there, even though the load's constant, it's going to oscillate. And I just said that too. And therefore we can get a fatigue failure just from running the shaft with a constant load on it. Same is true of transverse shear, because if I have a side load on the shaft, we know we're going to have transverse shear on that mid-plane, but now the thing's turning, so the mid-plane keeps changing. So, when the point comes through the mid-plane, it feels it, and then it goes to 0, and then back to the other direction, and then it goes back to 0, and so forth and so on. So I have the same sort of situation here, fully reversed shear stress. If the shaft is short, less than about 10 to 1 length to depth, then those shear numbers can be big enough to be of concern. Typically, with longer shafts, longer beams, the bending moments get really big because I've got a long moment arm for the force. And that starts to dwarf the shear stresses, because the shear stresses don't get big as I make it longer. They're independent of the length of the beam. Torsion, same problem. I can have a constant torsional load. Electric motor driving a generator, constant speed. The load is essentially just the drag in the generator from the flux generating electricity. And that's a constant torsion, but in that case, this point on this side of the beam is going to feel the same torque all the way around, isn't it? But if that torque changes, as it does in your case, because your cam is changing the load on that shaft's rotation, right? You go up and down the hill, you look at that torque function, it looks like a sinusoid. So in that case, I have a fully, well, maybe not fully reversed, more likely fluctuating, because I'm going between two values. In your case, you could be close to fully reversed, because you're going uphill and uphill and downhill. And if the uphills and downhills are the same steepness and the same load is present, then you could be fully reversed. But you could be anything else, because what if the hills weren't the same steepness going up and down? You've got a steep hill up and a shallow hill down, then your torque would not be symmetrical. So you could have any combination with a torque. And that will induce fatigue failure by shear. And of course, you'll combine any torque variations on that outer fiber with the bending variations. So now I've got a von Mises situation where the von Mises stress is going all over the place based on time. I showed you this picture before when we first started to talk about stress concentration. It's a shaft that has failed. We talked about these being called beach marks because they look sort of like the sand at the beach when the tide goes in and out, or I should say when the waves go in and out. And we believe that you need a crack to start a failure. Cracks typically are engendered by sharp corners. So here we have a keyway and a shaft. Somehow I've got to attach the gear or the pulley or the whatever to the shaft so I can transmit torque, right? Keyways are a common way to do that. There are other ways to do it. I can clamp the gear or whatever to the shaft with some very clever couplings I can buy at the store that essentially have a wedge effect. So imagine you have a conical piece. I got a two-piece gear now, and one piece is a cone tapered as it goes into the gear, and the other is a receiver with the same taper and a couple of bolts, and I just crank that thing in until, and one of them is split so they can bend in and grab the shaft. It's a collet. If you've ever used a lathe with a collet, that's what it is. It's a collet. And you can tighten it up as much as you want, and you can get a press fit up, that's really got a tight grip on that shaft. You say, okay, I haven't got a keyway, so I haven't got a stress concentration. No, that's not true, because where the load is suddenly applied, I have the analog of a sharp corner, and I got a fatigue concentration factor of about 2 at that point. And cracks can show up by mistakes made in fabrication. If they're there, they grow, develop around concentrations, and eventually they break the thing. Materials. Very few shafts are made of other than steel, unless you have some particular environmental issue. You'll notice there are 3 mentioned there: steel, stainless steel, and bronze. Bronze is popular for marine applications. It stands up against salt water pretty well. So does stainless steel, but it's a lot more expensive than bronze usually. So if you don't need the strength of the steel, the bronze is not as strong. You can get away with bronze for marine applications. But I would not go to either of these if I didn't need to, because I'm going to up the cost quite significantly over plain steel. So if I'm in an environment where I don't have water present on my parts, indoors, dry, heated, plain steel is it. And I probably don't want to go to super high-strength steel because I'm going to lose my ductility. I'm going to get more notch sensitivity, and I've got notches, keyways and such. So I usually am looking for maybe a low to medium carbon steel for the shaft. I can buy ground precision shafts, the first bullet there. And I can buy them hardened as well. There are some applications where I need high wear resistance. Some of you found those linear bearings, the round linear bearings, and you can buy those with a shaft that they're fitted to. And that shaft is hard and polished to reduce the friction and reduce the wear, and you can't do much to it because you can't drill it or tap it. So there's been a lot of investigation, some of it sponsored by ASME, which promulgates codes which sometimes are adopted into law by state legislatures, which will say, for example, the ASME boiler code is probably the most commonly known. So if you want to build a boiler, which is to say a furnace, or anything in which you're going to heat water and make steam, you would be very well advised to follow the ASME boiler code, which lays out in very great detail what the safety factor should be and how you calculate this and that and what equations to use and so forth and so on. And will give you a good chance of having a safe system. In similar fashion, the ASME some years ago did a study of shafts. And I haven't found much information on what drove this, and it's a long time ago. My suspicion is it was for shafts in power plants because they limited their case to constant torsion and fully reverse loading. And the only way I can get a constant torsion is to have a load that doesn't change. Your little cam is giving you non-constant torsion. And so if I was driving a generator set with a steam turbine, I got a very smooth driver and I got a smooth load, I'm going to get once I'm up to speed, I've got constant torque. Well, they did a whole lot of testing, and they tested the combination here of reverse bending stress and static torsional stress, which is to say constant torsion. And they also did reverse bending over here and reverse torsion. Those are 2 different sets of data. And they've normalized everything, so these scales go to 1, 0 to 1, and they're dividing by the fatigue limit in pure bending. That would be, of course, your S sub E, corrected for whatever factors were appropriate. And this would be your S sub ES. And over here it's S sub YS because it's static. So this is your endurance limit in shear, and this is your yield strength in shear for the static torsion case. And these dots represent failures for various, there's two materials represented here, two different stress concentration factors, 1.42 in bending, 2.84 in bending. Nickel, chrome, molybdenum steel, that's a pretty good strength steel. 4340 is a good high strength steel, one of the highest available in fact. Nickel, chrome steel, 3% nickel steel. And notice that, well, first of all, they fit a line to it, and it turns out to be an ellipse. It looks pretty much like a piece of a circle there because of the scale. But of course, if you put these back to non-normalized numbers, they wouldn't be the same length axes, and therefore it's an ellipse. So it's kind of your eyes being fooled here by the fact they normalized the data. So they've fitted a curve to the scattered data. Turns out to be an ellipse, but notice that there's a bit of scatter inside this ellipse. Not so bad over here, it's a better fit. But there's still, here's one breaking inside the envelope. So these envelopes are all created as your failure lines, right? And that's what we're going to design against. So this is called the GOUGH, G-O-U-G-H, after the guy who came up with it, just like the Gerber. We have a Gerber line, and a GOUGH line, and a Goodman line, and a Soderberg line, the guys that invented them, right? And here's the GOUGH line superimposed, the GOUGH ellipse so-called, which comes out of those shaft tests, superposed on my earlier diagram where I show the modified Goodman, the Soderberg, and the Gerber parabola. Now, to refresh your memory as to what I said about those three when I showed this to you before, the Gerber parabola is a good fit to the data, but it goes through the middle of the data, so there's points inside it and points outside it. The modified Goodman line more or less kisses the underside of the scatter. There's a couple that show up under it, not very far under it, but a few. The Soderberg, which runs down to the yield point instead of the ultimate tensile, they're all coming to the same point up there, your endurance limit or your fatigue strength at this number of cycles, yeah? They just end up at a different place over here. Soderberg must have been a very conservative guy because he put this thing under all the scatter. So every break that I've ever seen is above the Soderberg line. But it's now considered to be somewhat overly conservative because I'm going to put a safety factor under the Goodman line anyway. So I'm going to stay down here, right? By a factor of 2, 1.5, whatever you pick. So that gets me below the scatter. But with the Goodman line, we also have to worry about the fact that we might fail on the first cycle by yielding. If I had a very large mean stress, right, and a very not so big alternating stress, I get way out here. I hit the yield line before I hit the Goodman line. Well, Gough used the yield point as his terminus. So notice how similar to the Gerber parabola he is on the left end, and he dives down to the yield strength here like Soderberg did. So you don't have to worry about whether you're going to go out of this line or that line. It takes it all into account. But again, it goes through the middle of the data. So I think it's non-conservative. So the Gough and the Gerber are sort of the same animal. The Gough is to the Soderberg as the Gerber is to the modified Goodman. Straight lines versus curves. Conservative versus non-conservative. So I contend that the modified Goodman line is still a valid parameter to use for these shaft design problems. They're really the same fatigue problem that we've been talking about in general. I don't use the Gough ellipse. I prefer to use the Goodman. So for historical accuracy and collegial pressure by the reviewers of the book, who said, you've got to have the ASME thing in there. All right. So I put the ASME standard, which has now been abandoned, by the way. When I wrote the book, which is now pushing 20 years ago, it was still considered to be, okay to use. Since then, ASME has sort of disowned it, and for good reason. Because what it does is, where is it? It's assuming, well, I think I already said it, fully reverse bending and constant torsion. So it's a special case. It's a special case when I don't have any oscillation in my torsion. In my world, where I deal with machinery full of links and cams and gears, I never see constant torsion. I might see it in the power plant, but I don't do power plants. So I'm always seeing oscillating torsion of some sort, and oscillating bending is always there because even a constant load gives me oscillating bending, right? And I may not be fully reversed either because I might have some funny loads going on sideways. So anyway, what ASME's approach did is a good thing. They took all the messy formulas and combined them to get one design formula that says, what should the diameter of this shaft be based on the loads? And the loads in there are the M sub A, that's the alternating moment. T sub M is the mean torque. Those are the main factors here. We've got some stress concentration factors, K sub F, SM mean. We've got some S sub F, which is my strength and fatigue. S sub Y, my strength and yielding, because that's a static case. And we've got some constants out here. N sub F is my desired safety factor. So this is running it backwards. I want a safety factor of 2. What's the diameter going to be? That's a good design equation because it's going right to the chase. Give me the diameter I need for the shaft. I want a safety factor of 2. And these are my material properties. And we got some powers sprinkled in there. No problem with a calculator or a computer to do that. I groaned when I had to do that on a slide rule as a young man because these things are not easy to do on a slide rule. Got to do logs. But piece of cake in a calculator. So here is, I think, the better way to do it because I've got everything in here but the kitchen sink. I've got, I can accommodate fluctuating bending anywhere to anywhere, fluctuating torsion anywhere to anywhere, doesn't matter. I've got more terms. I've got MA, that's the alternating moment. I've got MM, that's the mean moment, if any. If it's not there, you just make this 0, and it reverts back to the earlier equation. Right? Here's TA, alternating torque. Here's TM, mean torque. So it's all in there. SUT, never mind this SY business. We're using Goodman here, not Goff. That other one uses Goff, by the way. The ASME standard uses the Goff line, which, as I've already pointed out, is not conservative in itself because it's through the scatter of the data. So I'm using S sub F, which is my corrected fatigue strength for whatever number of cycles I care about today. NF is my fatigue safety factor that I would like to have. The stress concentrations appropriately manipulated. You know, K sub F is going to involve the Q and the K sub T. K sub F, S for shear. We'll start with a different K sub T and bring in the Q, manipulate that. K sub F mean, we talked about that the other day. That's when you say, well, is it going to yield or not? If it's going to yield, I'm going to relieve some of the stress. I can cut down my K sub FM, back and forth. Okay? By the way, the ASME sets this to 1. It doesn't apply any K. Another problem, in my opinion. K for the mean, and turn the crank and get your D. So a very handy design formula. Choose your material, figure out your loads. That's the hardest and most error-prone part of the problem. If you don't get the loads correct, you stand up prayer at getting the stresses correct. So it's very important to do your load analysis right, which is why I'm saying free body diagrams. You cannot know what your loads are if you don't have a proper free body diagram of the system. And if your loads are bad, your stresses are worthless. So that's pretty straightforward. So let's spend a little time going through one of the examples in the book, 10.2 to be specific. And I got sort of a mishmash of stuff here. I got a gear and a pulley, some steps in the shaft, a couple of keyways, and I'm going to make up some numbers about what the loads are on this thing. A couple of ball bearings here, so I got a nice simply supported shaft, so that's easy enough to do the diagrams on. I've got loads in the belt, a V-belt by the look of the pulley, And so this is the tight side, so I got an F1 in the tight side and an F2 in the slack side, and what this guy feels down here is the difference. Horizontally, I got a reaction force to hold the thing up, and I've got an FG, which is the force on the gear. Now, gear teeth, you recall from kinematics, have pressure angles, just like cams, and they're standardized at 20 degrees or 25, typically, in the U.S. And so I've got a force at some funny angle at the gear tooth, and I've got to resolve that into X and Y components. So I've got a 2D case. I've got loads in the X, loads in the Y. I have to draw diagrams for both. So I've got to do loading, shear, moment, slope, deflection in the X, Z plane. I'm calling this shaft axis Z, and also in the YZ plane, and ultimately combine them with Pythagorean theorem because the shaft doesn't give a hoot about X, Y. It just is in its own little world. So I've got to find out what's the largest force, moment, et cetera, on the shaft, right? But it's much easier for us to cut it off, cut the cat's tail off small piece at a time. It doesn't hurt the cat so much. So we do the X, then we do the Y, and just put them together with Pythagorean later. I was thinking the other day, walking to my car, how many times has Pythagorean's name been said since, where do you live? 100 BC or something like that? You know, what a thing he did for us. But that simple little equation, how much we use that as engineers. You couldn't live without it. Okay, here's the data. We got some mean and alternating torque. They're both 74 pounds, so they're both fluctuating. Pound-inches, I should say. I want a 2.5 safety factor, infinite life. I'm going to use a cheap steel with good notch sensitivity. Room temperature, 2 horsepower being passed at 1750. And I'm going to assume some stress concentration factors here. And there's an interesting, well, I won't go into that right now. We'll see that later. I'm going to pick some numbers just to get things going. So you could get a better number by going to some of the Peterson tables. So I'm saying 3.5 in bending, 2 in torsion, 4 at the keyway. Those are realistic numbers. So this is telling me that we have time-varying stuff in both torque and moment. It's repeated. We talked about the numbers already. No applied axial loads. Now, if this shaft were vertical, then I could have some serious axial loads because this stuff's big. So if I got that gear hung on the shaft or a flywheel or something like that, it's pulling down on the shaft by gravity. Then I wouldn't ignore the weights of stuff. I'm not going to include the weights of the shaft and stuff in this because they're small typically compared to the dynamic loads if I'm running at any significant speed, if it's horizontal. But I might have a third direction stress, not third direction, but another component, axial, if I were vertical. And there are plenty of vertical shafts around. Think of water turbines. Most of those are vertical and they're big, and they spin fairly fast for their size. So the first thing I have to do is try to figure out where should I direct my attention at this system. I only have limited time to solve this problem. I can't solve it for every bloody point on that shaft. I got to pick ones that I think are the most vulnerable. Well, right away I'm going to be attracted to any places of stress concentration and some significant moment. It helps to have the moment diagrams to look at while you do this, and I haven't brought them up yet, but I will in a minute. So I'm looking at stress concentrations, and I've labeled 3 points, B, C, and D. B is here in the keyway, and that's, I'm saying, has about a 4 stress concentration factor. And C is at the step right here where I have a change in section. And I'm going to have trouble getting a big radius in there if I want to jam that ball bearing up against it, because the ball bearing has a very small radius on the edge. I can do some tricks like relieving it, and like you saw in an earlier slide, put a washer in there with a bevel and so forth. I'm not bothering to do that right here. And then I have another point, another keyway here, and actually I have a D is at this step. And here's another keyway. Why do you think I didn't bother with a point E at that keyway? Any suggestions? Why that is not critical? Very little moment. Moment comes to 0 at the end of the shaft. I'm almost at the end of the shaft. In fact, this point might not even be too bad because the moment's going to be smaller. All right? So you're absolutely right. So here are the torque and moment diagrams. So I've got a mean torque, an alternating torque, a mean moment, alternating moment. If I add them together, I can look at the peaks here. So I use the beam equations so I can get, I'm only going as far as the moment here. I'm not going to bother with deflection in this example, I think. So I write those three equations out with the singularity function. Z here is my dimension along the shaft. It's common in mechanical engineering, by the way, in systems of this sort, to use the Z axis for the rotational axis. It's just fairly standard convention. There's no law about it. You can call it whatever you like. But you'll often see Z for the direction along the shaft. So I got to pick a material for trial. I pick 1020. I get the SUT and the SY out of the tables. I calculate my S sub B prime, which is half of the SUT. I get 32.5. I sprinkle in the factors. Now here right away I have a problem because, well, C load is bending, right? 1 is bending. But I got torsion in there. Why am I not accounting for the torsion in the C load? Well, the answer is I'm going to go to von Mises, and I'm going to convert the torsion into fake tensile stress. And so I can consider everything to be tensile once I'm in the von Mises domain. So my C load is 1. I don't know the part size. Here's the problem. I'm trying to find this diameter of the shaft. So how do I get a C size factor? Ignore it for now. Call it 1. I can always go back and trim it with another calculation. Yes, sir. Yeah, exactly. Yeah. You could, if you wished, apply a 0.577 for the torsion and compare it to a torsional strength, which would be 577 times the tensile strength. But, you know, it's a wash. My stress is 0.577, and so is my strength. Right? So that's just extra work, in my opinion. So if you take everything to von Mises, it makes it easier. Right? So you understand what I'm doing here. I'm saying I will worry about C size later. C surf I pick for machine because I know I'm going to machine this thing. Temperature doesn't matter. Reliability, I picked 1. I said the other day that I wouldn't really use 1. That's 50%. But I'm just doing a first pass through this thing. I can go back and trim those to tighten it up anytime. Particularly if I set this up in TK or MathCAD or whatever, it's just a case of tweaking a number and running it again. So I'm going to set it up as simply as possible. I can get the notch sensitivity because I picked the material. In one of your homework problems, I think you're trying to find the material, aren't you? So in that case, I can't figure out the Q. So I just say, well, the hell, Q is 1. Just assume it to be 1 and turn the crank and get a material that looks good. Then I can run back through, and now that I know the material, I can apply the Q, and it'll make me a little bit better, a little bit higher safety factor. So I'm being conservative when I take Q as 1. And when I make these assumptions, I'm usually going on the conservative side. This is an exception because if it's anything bigger than 3/10 of an inch, it's going to be less than 1. Okay, so I can get the Q, and I can, and they're different in bending and torsion. And I'm assuming a notch radius here of a 10,000th of an inch, which is a pretty tight corner. And that's commensurate with what's on the ball bearing. If you look at a ball bearing drawing, you'll see you've got about a 15th thou radius, I think, on the corner. So 10 will clear it. So we do the usual calculations with the Q, and we get a 2.25. We factor the 3.5 down by quite a bit because it's a low notch sensitive material. It's only a 0.5 Q. So we take away 2/3 of our K for the fatigue calculation. The shear, we start with a different number of 2, and we knock it down about 1.5. And this refers to the fact that I'm going to check the maximum stress to see if I go above the yield point or not, and I don't. So that means I use the full value of the K sub F on the mean side, too. And then I just get out the crank and I turn it. And I put all that stuff into this equation. and turn the crank, and I do that for each of the points, point C, point B, and point D in no particular order. And I get these numbers, 0.614 inches, 0.632 inches, 0.512 inches. Those should be considered minimums. I can make them bigger, certainly. I use 2.5 for the safety factor, which is a very comfortable safety factor. And I'm making it comfortable because I got a whole lot of question marks in this thing at this stage. I can always tighten that up later. So I can show these things on my Goodman line to see what I actually have for safety factor in each case, which should be between 2.5 and 3 over here. This should say 10.1 and 10.2, by the way. I changed the chapter numbering between edition 3 and 4. So here's our, I'm assuming case 3, by the way. I should have reinforced that. Both of these equations, these D equals equations, both the ASME and the more general version that I show you here, they are assuming a case 3 situation. That is, as time goes on and the loads change, the alternating and mean go up and down together. And I don't know really if that's true, but that's the assumption I'm making. So somewhere in here, I didn't put it in the slides, I rounded these up to standard sizes. I can't buy a shaft with a .632 diameter. That's an oddball number. So I think I rounded that up to 3/4 of an inch, 0.75. That's the biggest diameter on the shaft. If I buy cold rolled or cold drawn steel, 3/4 inch diameter, the finish is good enough to just use as is. I don't have to machine it. I got to machine it down to the other dimensions. But now on that 6.1, I think it's this guy here, 614, there's a bearing there. And so I went to the bearing catalog and I got the closest bearing I could to .614 for an ID. And it turned out to be 17 millimeters. And I converted that back to inches, and it went up a little bit from 614 to something else, and so forth. So I'll tailor these now for practicality to fit standard parts, standard bearing diameter, standard gear diameter, whatever I'm trying to put on the shaft. Okay? So this is just my starting point for my minimum. And as an aside, I mentioned that the bearing diameter was expressed in millimeters. There's some interesting history to that, which goes back to the early days of the automotive industry, both here and in Europe. And we're talking now 1900 to 1920 type time frame. And ball bearings were invented around that time. They were invented a little bit before that, I think. And when they were first invented, the ball bearing manufacturers got together and agreed on a set of standards. And they decided to make them metric. So that ball bearings have been standard metric for over 100 years, both in the U.S. and overseas. And that's a really good thing, because it turns out that you can go back. I have a friend who restores antique cars, and I've done that myself in my lifetime. I don't do it anymore. And he will have a car made in 1907, and the bearings, of course, are shot. And he will mic the bearing to get the diameter, go to a bearing catalog, and he can find the exact match in 2007 for a car made 100 years earlier, because the bearings have been standardized and the standards haven't been changed. Now the standard there refers to the OD, the ID, the width, so you could drop it in. The guts are very different, because they know how to make bearings much better now than they did 100 years ago. So the material's different, the internal details are different, the ball size is probably different, almost everything is different and better. But the outside diameter, the inside diameter, the tolerances for the press fit, and the width of the bearing the same as they were 100 years ago. That's really handy. So I went through this rather rapidly. This is laid out in more detail in the book. You're going to have to read the book, I'm sorry to say. And there are several of these examples, and we're going to do another set of them next time we meet for a lecture, which is Shaft Design 2. Which is the second part of that same chapter.